Hi there. Occasionally, I need some higher DC and AC voltages. Well, who doesn't, right? And right here, I have to warn you that with these voltages, you need to know what you're doing, and if you are following along, you do so at your own risk. In my case, I need those higher voltages for testing and calibrating of multimeters, and some time ago, I made this high voltage DC to DC converter. It is quite useful and pretty stable after a minute or so, and produces a very clean DC, but sadly only between 85 and about 210 volts. Sometimes I need a bit more. There are plenty of cheap DC to DC converters, and this one is an example. It's a timer 555 driving a power transistor to pulse a transformer. The output gets rectified and boosted in a voltage multiplier. While this can produce quite high voltages, the control and stability is poor, and there is quite a ripple on the DC, shown here on the upper readout as AC voltage. It's okay for a rough test, but not much more. There are other ways. You can use a regular transformer to create a high AC voltage and then rectify and smooth it, or simply buy yourself a used electrophoresis power supply from eBay. I went another way because per chance I saw this module on eBay, very affordable, and on a whim I bought it, thinking that surely a well-known manufacturer like Start Spellman will have manuals. Spellman's high voltage power supplies are pretty high-end and normally used in expensive scientific or medical devices. 3 kilowatts from 24 volts DC is way more than I would actually need, but it can be set to produce lower voltages too. It has two short high voltage cables attached. On the top is the pinout for the input, which includes a voltage monitor and control, exactly what I want. All the inputs and controls are on a 9-pin D connector. My ultimate plan is to add a 24 volts power supply, a knob to adjust the output, and a meter to show the voltage. The lid is held by 4 screws. But there isn't that much to see. Most of the interesting high voltage part is completely potted for obvious reasons. Just the low voltage end of some transformers stick out. A closer look on the part that is visible. The red insulation on the transformer is probably the primary side with a few windings of relatively thick wire. The white caps hint on some kind of snapper network, and the big MOSFET switches it. Obviously, the low voltage circuit creates an AC voltage for the transformer, and in fact, the Spellman literature on their website indicates that the potted part contains probably a multi-stage high voltage multiplier. So this is really just a big version of the little board I showed earlier. Obviously it has proper filtering and feedback for monitoring to enable proper control and regulation. I pretty much drew a blank searching for downloadable manuals or even datasheets for my unit. Upon contacting Start Spellman, they explained to me that this is because my unit is from a batch made specifically for a customer, and Spellman can neither reveal who that customer was nor release any documents. By good luck, I did find a lab manual for engineers at some facility mentioning the part number of my power supply. I would like to tell you which lab, but I did not note down where I found it, and it apparently is no longer online, so at least I can't find it anymore. The manual is full of acronyms without explaining any, but my guess is that my unit was powering the MCP, which might stand for microchannel plate detector in a thing that does TOF, probably meaning time of flight in some mass spectrometry setup. At least the voltages down there look within the limits. Whatever MCP really means and what it was used for, the helpful section was this one. The control is a DC voltage from 0 to 10 volts, with 10 volts meaning 3 kilovolts, and the monitor readback line is 0 to 5 volts, with 5 volts meaning 3 kilovolts. Another hint is to add a series resistor of 1 kilo ohm in line with pin 2, so I will include that into my setup as well. I rigged a quick test setup. The large red multimeter on the left is measuring the high voltage using my divide by 1000 probe, which is the black box on the far left. So the number on the meter display is really kilovolts. The other multimeter on the right is measuring the monitor voltage. I wired a 10-turn pot on the right as a voltage divider to feed a variable DC voltage between 0 and 10 volts into the control input. As the control voltage increases, the output voltage rises, and so does the monitor voltage. I show this sped up because I was stopping every so often to record the readings of both meters. The result is this graph here. The fact that the traces have this kink is because I was not very careful to always increase the voltage by the same amount. The important fact is that they both are nearly on top of each other. That means the monitor voltage is a true representation of the output voltage. That's great news because I do want to add a meter showing the output voltage, and measuring 0 to 5 volts is far easier and safer than measuring 0 to 3000 volts. My first choice was using one of these inexpensive analog meters I had lying around. The 0 to 30 volt scale could be easily read as 0 to 3 kilovolts, if necessary handwriting a K in front of the V and put some decimal points between the numbers. Reading the current through the meter at full scale shows that this is really a 1 milliamp meter with a 30,000 ohm series resistor inside to measure 30 volts. I opened it and temporarily removed the blue wire from the resistor and connected it directly to the terminal. This allows me to use my own resistor, which for 5 volt full scale should be about 5 kilo ohm. But that did not work too well. The modified analog meter is above the digital one on the right, and they are both in parallel. At 1 kilovolts, the monitor voltage should be 1.6 volts, but it's just 0.56 volts. The reason is that the 1 milliamp current draw by the analog meter loads the monitor output so much that the voltage collapses. I need a different solution for the meter that draws less current. I still had a 50 microamps meter of the same type, and with a 100k series resistor, it now reads 0 to 5 volts. At 1 kilovolt, the monitor voltage is 1.67 volts, and that's roughly what this meter shows. I found that instead of 100k, using a slightly higher series resistance of 103k makes the meter track more accurately. This is because the 50 microamps are still loading the monitor output a little compared to the negligible current through the 100 megohm resistance of the digital meter. At 1500 volts, which is half of the max voltage, the pointer of the analog meter showing the monitor voltage should be right in the middle of its scale, which it is. At 2400 volts, which is 4/5 of the max voltage, the meter should be on the 4 of its 1 to 5 scale, and it does. So this solution would work, but of course I don't really want to see a 4 on the meter, but 2.4 kilovolts. So I decided to park the solution for now and look at a digital alternative in form of the now ubiquitous panel meters. To be usable for this job, a panel meter has to be of the 3-wire type, like this one, meaning that its operating voltage feed is separate from the voltage to be measured, both referenced to a common ground. I ran a quick test with 2 of these panel meters. The lower one, with 4 digits, has a trim pot, and I calibrated it to show 3 volts as accurately as possible. Right from the start, there's an obvious problem on both. They are quite a bit off at low voltages, and the 4-digit one did not even show anything until at least 0.25 volts has been exceeded. When scaled to the monitor output, that means voltages below 150 volts are shown as 0, which is unacceptable to me. Raising the voltage further shows that it takes about 1.5 volts, which would be the equivalent of 900 volts, before the accuracy of the lower 4-digit meter approaches acceptable values, while the upper 3-digit meter only really gets going from 4 volts or equivalent 2400 volts onwards. Maybe a quick word on how to adjust analog or digital meters so they show the voltage range you want. For analog meters, it's pretty straightforward. They all measure current, for example 50 microamps full scale. R series is simply the desired voltage at full scale, 5 volts in this case, divided by 50 microamps, or 100k. Actually, for more accuracy, one should determine the coil resistance and subtract that from R series, but for those cheap meters the coil resistance is normally not very high, and the large mechanical and electrical tolerances usually don't justify getting overboard with accurate series resistors. For digital meters, a different approach is needed. To make them show 3.00 volts when Vmon is 5 volts, which means 3 kilovolts at the output, it is necessary to use Vmon through a voltage divider. Digital meters usually have a fairly high input resistance, R input, in the order of megohms. I added the formula to calculate R1 if R2 is given. One needs to choose R2 low enough so that our input is at least 10 times higher to allow it to ignore it. On the other hand, R2 needs to be high enough so that the voltage divider does not load V1 too much. For example, you can choose R2 to be 120K, then R1 will be 80K. I have another high accuracy panel meter, but that one measures just 0 to 200 millivolts. Using the voltage divider principle just discussed, the meter can be set up to use V1 for displaying the output voltage up to 2 kilovolts. The problem with this meter is that the highest value it can show is 200 millivolts, so it will overflow beyond 2 kilovolts. I can, of course, make the voltage divider to show only 30 millivolts for 3 kilovolts, and everything fits into one range, but the accuracy is poor and it gets worse for lower voltages. Anything below 100 volts will just show as 0. So back to my analog solution with a 50 microamp meter, which needs a new scale to be usable. My first idea was to replace the 50 microamp scale with that of the 30 volt meter. Of course, that would mean to sacrifice that 30 volt meter. But then I thought, why not use the 0 to 30 volt scale as a template to make a new one for the other meter. That way I can put the original scale back when the job is done. Although the real scales are made from thin metal sheets, I decided to try simple printer paper and printed a couple. Here's a comparison of the original scale and my cutout replacement. First I tried to replicate the complex cutout at the bottom, but that turned out to be very tricky and the needle got stuck easily. So at the end I simply made a squarish cutout that stays well clear of the needle movements. The new meter ready to show kilovolts. With all the fuss about the meter, I have not even touched the rest of the build. Still lacking a 3D printer, I made 4 wooden legs that each have a machine bolt epoxied in. The purpose of these wooden legs is to raise the Start Spellman power supply module. And the sole reason for doing this is so that a fairly long analog meter body fits underneath, because as you will see in a moment, there's very little space in the enclosure. This is how tight the high voltage module sits in the enclosure. It may look as if there is space, but this type of enclosure has internal plastic columns to connect the 2 half shells that get in the way. Here's a mock-up of how the rest of all the gear is supposed to fit. From left to right we have the output sockets, the meter, still without its new scale, the 10-turn pot to select the output voltage, and an illuminated mains on-off switch. All the front and back panel items have been installed. On the back is the power inlet with integrated fuse and a small 24 volts DC switch mode power supply. The high voltage part draws less than 150 milliamps at 24 volts, so the power supply does not need to be very big. I got lazy and the 10 volt supply for the control voltage is simply a 3-pin voltage regulator with a necessary cap soldered directly to its pins. I added a resistor into the 24 volts input to reduce the drop over the regulator. The reason is that my 10-turn pot has only 470 ohm resistance. That's what I had in the parts bin, but a better choice would have been a 1K or 4.7K or even a 10K pot because it wastes less current, but I would not go any higher. The basic power wiring is in. Most of this will be hidden under the high voltage module once that's installed. Which means now is the time to test if that part works as it should. The 24 volts power supply works, and so does the light of the power switch. And the control voltage can be adjusted too. I hooked the meter temporarily directly to the control voltage to see if it works after it had its scale replaced. Seems to work just fine. In a first test, the Bryman 869S and the Kaiweets HT118E are both connected in parallel directly to the high voltage power supply without any divider probe, which means I have to be careful not to go much higher than 1000 volts. The Kaiweets starts to beep if 1000 volt is exceeded and then died. Wow, that was very unexpected. Actually, all that happened was that the red danger backlight the Kaiweets is turning on above 80 volts and the beeping that started above 1000 volts simply exhausted the battery. With freshly charged batteries, the Kaiweets HT118E is of course able to measure 1000 volts and slightly above. This, by the way, would be how you do or check calibration with this power supply. You need to measure the voltage with an instrument that you trust and is more accurate, and then use that value to adjust the other meter. So far so good, but then I realized I've forgotten something. The high voltage output on this power supply is floating with respect to ground. So far I was always testing handheld meters, so that did not matter. A quick look at bench multimeters, however, reveals that all of them impose restrictions about the maximum voltage difference on their inputs with respect to ground or their guard terminals can be, and it's far less than the 1000 volts the meter can usually measure. Take the venerable Solartron 7050, which limits its guard terminal to be a max of just 400 volts above ground, and the difference between guard and low can only be 100 volts. Why can this be an issue? With the output of the power supply floating, there's really no way of knowing how high the voltage above ground is for either positive or the negative terminal. All I can set is how much higher the positive is relative to the negative, say 1000 volts. Some older multimeters use an external guard connection to help reducing measurement errors caused by a common mode voltage. This diagram from the Solartron 7150 Plus shows this concept well. Normally, the measurement section with its high and low terminals is floating. If there's a high common voltage VCM, it can cause problems because a current flows over the low terminal through unavoidable leaks to ground. This current causes a voltage drop over the low measurement lead resistance, and if the resistance and VCM are comparatively high and the to be measured voltage low, that voltage drop can cause noticeable interference in the measurement results. The remedy is to connect the guard terminal to the source of the common mode interference. That way the current is diverted and can't cause interference. This raises the question why modern meters don't have a guard terminal. While connecting an external guard terminal is probably the best way to suppress common mode interference, it's inconvenient to use 3 measurement leads, so they use internal ways to do a similar thing, and that works good enough. Even the Solartron 7150 Plus already has a built-in circuit that consists of an RC network that is adequate for most cases, so you don't have to use the guard terminal. However, these capacitors have a max voltage rating, and this is where one has to pay attention to not damage the multimeter when high voltages are involved. There is an obvious limit of how much voltage can be tolerated between the low and guard, between low and ground, and between guard and ground, while the limit between high and low is the 1000 volts or whatever your meter can measure as max voltage. I decided to add a green binding post connected to mains ground. With a patch cable that allows grounding of either the positive or negative high voltage output. Like so, when I want to test multimeters for max positive voltage. This configuration ensures that there is no voltage between the multimeter low terminal and ground. To test for max negative voltage, the configuration would be this. Now the positive high voltage is grounded and connected to the low terminal. And the meter, of course, now shows negative voltage if it's working correctly. To complete the video, this is the final schematic. A small switch mode power supply provides a stable 24 volts DC voltage for the high voltage module. This 24 volts DC also feeds a simple circuit consisting of a 7810 voltage regulator. The 10 volts output is connected to a 470 ohm 10-turn pot that provides a control voltage ranging from 0 to 10 volts. The monitor output is connected via a 103K series resistor to a 50 microamp analog instrument, and that's all there is. I did notice that you need to run the power supply for at least an hour before the voltage gets really stable. Once it has warmed up, you can change the desired voltages and it stays there quite well. If you like my videos, don't forget to subscribe. There are more projects, repairs and reviews coming up. And it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.